So I want us to first of all do number 1 and then number 2. Number 1 says 2 identical beakers, each of mass m, are attached. I believe we can see the beakers. It's important to see the beakers. These are the beakers. They are attached to each other using a string. There is the string suspended from a pulley. We have a pulley there. The beakers are held at rest at a height h. So this is the height at which the beakers are held at rest above a surface. Cooking oil of volume V is added to one of the beakers. So into one of the beakers, we're going to put cooking oil of volume V. The beakers are released so that the beaker with the oil begins to fall. It's only natural since the beakers are identical and they've got the mass capital letter M. If we add oil into the other beaker, then it becomes more heavier, meaning that it is only natural that it is the one that falls down whilst the other one will be going up. The speed of the beaker as it reaches the surface is Z. So this there, remember, is our surface. So the speed as, let's say this is beaker here, reaches the surface is equals to Z. It is suggested that Z is related to V by that relationship where A and B are constants. Plan a laboratory experiment to test the relationship between Z and V. So we want to test the relationship between Z and V. What are we testing? We are testing whether the suggested relationship is correct, is valid. So that's what we are testing. We are doing an experiment we are designing an experiment such that once the experiment is done, if we obtain values of Z and V, then in this experiment and the analysis that follows, a person can be able to ascertain whether this relationship is correct, which was suggested to be the relationship between Z and V. And also explain how your results could be used to determine A and B. So all of this is important. So ultimately we need to explain how our results will be used to determine A and B. And with A and B, A and B are part of this equation. So we will need to show that our results from the experiment of V and having done the experiment and the analysis, how we are going to be able to determine A and B. Okay, let's move on now. I have already done this question, written it in advance so that we don't waste time. So the first things first is to state the variables. Which variables? Number 1, the independent variable. Number 2, the dependent variable. Now, how do we know who is the independent variable? The independent variable is the one which ourselves we are adjusting. Then the dependent variable is depending on the change in the independent variable. So I believe in this case, we can agree that the speed with which the beaker reaches the surface depends on the volume of the oil that has been poured into the beaker. So V is the independent variable and Z is the dependent variable. Now next, the question is, what must we keep constant? Now to determine what we must keep constant is not that tough. Here I do not write it correct. Okay, it's here I said keep H constant and M constant. How did I know that it is the things that must be kept constant? For example, we are already told that A and B are constants. So if I go into this relationship, we're investigating Z against V, and A and B are already constants. This leaves in this equation two things. It leaves H and M as the only things that we don't know whether they are constants or not. But since we want to investigate Z and V, and we know that A and B are already constants, we must make H and M also constant to ensure that our relationship that we'll be investigating will just be between V and Z without the influence of H and M. We don't want H and M to influence the experiment. So it is important to tell us what we are going to keep constant. So in this case, as I said it here, keep H and M constant. So to describe the procedure now, you need to be clear how you describe the procedure. Firstly, in my own opinion, which is a very good opinion, to describe the procedure, you must first of all tell us what and how the experiment is performed. For example, you must tell us how everything is going to be done if we have those apparatus, such that we are able to measure the independent variable, such that we are able to measure the dependent variable. What must be done such that we have even the independent variable? Because we can't measure the independent variable that we do not have. We must have the independent variable, and afterwards we must have the dependent variable, because it is pointless to have the independent variable and not have the dependent variable. So the first part of the procedure is describing how you are going to have the independent variable and how you are going to measure it, how you are going to have the dependent variable and how you are going to measure it. So for example, I say here, pour oil from a jar into the measuring cylinder to note the volume V. So I forgot here to write it correctly. It was supposed to be into the measuring cylinder to note the volume V. So I've already said the two things here. I've said that we are going to measure the volume, number one. Still, I'm continuing. And pour this oil into the beaker whilst holding the beaker. So I've explained the process of us having an independent variable. The independent variable is the volume V of the oil in the beaker. So ultimately, at first, we did not have oil in the beaker. So I went ahead to explain how we are going to have oil in the beaker of non-volume. So we would have measured this volume with a measuring cylinder. So you see. Then the next part now, I talk about now how to have the dependent variable Z and how to measure it. Release the beaker here. Release the beaker with oil from the two light gates positioned as in the diagram and connected to a data logger. Note the time t to fold the height h. Using the equation, this one, find the speed z with which the beaker reaches the ground width. So ultimately, this culminated in us being able to find the speed z. So the entire part starting from here was intended for us to have the dependent variable. For example, we cannot have the final speed of which the beaker is reaching the surface if the beaker doesn't move. The beaker has to move. And then I described the processes in which we are going to be able to measure things which will allow us to determine the speed z as it reaches the surface. But however, the process of us having the dependent variable and then the process of measuring the dependent variable is what I did here. So that's why you will see that I put the first star here. It indicates this point. The first point that you must focus on in this question is how am I going to have the independent variable and how am I going to measure the independent variable. Then the next part of that statement is how am I going to have the dependent variable and how am I going to measure the dependent variable. So I must explain here the process of having the dependent variable, which I have highlighted right now, and measuring the dependent variable. So we are releasing the beaker with oil. So what do we do? From the two light gates positioned as in the diagram. So we have two light gates here. So you see now this is the position of the beaker. Let me put an X like that. So we have the light gate, the first one here and the second one here. So a light gate, how does it exactly work? That is the major question. In my diagram, I didn't put another light gate here. They work in conjunction. It's not just one light gate. They work in conjunction I didn't put the other light gate. Okay, so these are the light gates. There are two of them. There are two of them. And how do I mean there are two of them? This is one light gate. This is one light gate. When I say one, what I mean is that when this one produces light, this one detects the light, such that when the beaker passes through and breaks that light, the light gate, which detects light, will not detect light, and it will send information to this data logger, and the data logger will start the stopwatch. Now, and this one also is producing light, this one is detecting light. So when the beaker arrives and breaks the gap between the two, what will happen now? There's no more light arriving here. So this one detecting that there's no more light, it sends the information to the data logger to stop the stopwatch. So that's how a light gets back. So if you understand that one, then we can proceed. This is how light gates work. So now, why are we using light gates to find time? Because usually to measure time using a stopwatch and the time for which the beaker is falling there, the time is so small. Us using a stopwatch, we introduce tremendous errors to measure the time exactly as the beaker starts to fall and exactly as the beaker arrives at the ground. Usually we'll be doing it in the physics lab, and the distance and the height is too small for us to be able to start and stop without introducing a significant error into the reading. So that's why we prefer light gates, because they'll give us the actual time taken to move from height h until it arrives at the bottom, at the surface. So having found time, then how did I explain everything else now? Because it wasn't just about finding time. It wasn't just about finding time. How do I explain this part here? Now that we find time to fall through the height h, of course the height h we already know it. So where does this equation come from to find the z? This equation comes from knowing that the initial speed of the beaker is 0. So knowing that the initial speed of the beaker is 0, we can use the equation s is equals to u. Okay, here we want to find the final speed, sorry. So we must use a different approach here. So what we are simply doing here is, sorry, okay, so what we're simply doing here is this. We know this equation which says s is equals to u plus v over 2 multiplied by t. So this is the only equation without acceleration. Since we don't know acceleration here, this is our choice of equation of motion. So we're also assuming that acceleration is a constant, because it works only if acceleration is a constant, even though we don't know the acceleration in this case. So what do we do next? Our s is the h, but initial speed is 0. Final speed is z. This is what we're looking for, over 2 times t. So I divide both sides by t. This gives me h over t is equals to z plus 0 is z over 2. So I multiply both sides by 2. So this becomes 2h over t is equal to z. So the final speed with which we arrive at the ground there can be found from that equation. So all we need to know is h. Now, how do you measure h? H is measured using the meter rule. So I forgot to indicate it here. You don't just tell us how to measure time and not tell us how to measure h. The height h measured, you must tell us how you're measuring everything. Measured by a meter rule. As simple as that one, but you must tell us how you're going to measure h. I had not said it there. Okay, so now this is just how we find the speed z and how we find phi. So having explained how we are going to have V and how we are going to have Z, we need now to explain how the experiment is continuously performed now, because we never do an experiment to just have one set of reading, one value of volume V and one value of final speed Z. So we must tell us how we are going to have more values of V and Z. So that's when it comes here where I say vary V by using different volumes of oil as measured by the measuring cylinder. By using different volumes of oil as measured by the measuring cylinder. So we are going to vary V. So each time we are going to add more oil, or we are going to remove the oil that will be there already in the measuring cylinder, because when it falls, there's a chance that in a single experiment there might be some splashing and the like. So we might actually need to empty the beaker, and after emptying the beaker, since it is falling, and as I will tell you, it falls into a sand tray, there might be some sand attached and the like. So we might need to actually ensure that we are measuring V correctly. So we have to pour oil at each time. So we are varying V by using different volumes of oil as measured by the measuring cylinder. Then for each value of V, obtain a value of Z until you have 6 sets of readings. Okay, that is fine. Then finally, the final step of the 3 stages of this procedure, which you must always write, is how to keep what we say to keep constant. For example, how to keep the height constant. How do you ensure that the height from which it is falling, or which the beakers are falling, is always kept a constant? So here I say keep the height h constant by measuring using a meter rule that is vertical, and by use of a set square of the bench. So our meter is already vertical, as you can see here. I drew this diagram afterwards, after I finished the question, but here, as you can see, our meter rule is already vertical. How is it being made vertical? Because on the workbench we have put a set square that is labeled in green there, and that set square and the meter rule makes it vertical. So by measuring, by ensuring that the meter rule is always kept at that level, we are able to know exactly where we are not able to know exactly where the beakers are, and keeping the height h from where they fall constant. Then ensure, we also need to remember M constant. How do you ensure that M is constant? The mass of the beakers. Because remember that the mass of the beakers, there might be some things that might change it. For example, if you pour oil in a beaker, there's a likelihood that even if you remove that oil, some oil will be stuck to the surfaces of the beaker. So when you add new oil, the volume might be more than the actual volume that we want. So what do? We must always measure the volume of the beaker after each experiment, the mass of the beaker after each experiment. But how do you measure the mass of the beaker to ensure that we know the mass of the beaker? And not only do we want the mass of the beaker for the sake of keeping the mass constant, we also need the mass of the beaker because we will need to find the constants A and B. And in that equation, to find A and B, the mass of the beaker must be known. So how do you find the mass of the beaker? By measuring the mass of each beaker using a top pen balance. Okay, next is the analysis stage. Now analysis stage is the stage where we decide what graph we must draw, since we have 6 sets of readings, to be able to obtain the things that we want to obtain. So this here is the equation that we are given, and as it is the equation that we are given, then the next stage is, if this is the equation that you have been given, what graph should we draw? That would be a straight line. So first things first, I divided everything, as you can see here, I divided everything by 2h by 2h. Here 2h was here, then I was left with 1 over z squared. Now since my relationship that I want to find is between z and v, you can see that it's 1 over z squared on the one side here, and here it's 1 over v. So it's perfectly fine for me, because as it stands here, if I put on the y-axis 1 over z squared, and on the x-axis 1 over v, then the graph, if this equation is valid, then the graph of 1 over z squared against 1 over V must be a straight line. Suppose this is a, so now using our readings, that, remember we are just testing this relationship whether it is correct, because it is a suggested relationship. So how are we testing it? By doing the experiment to get values of Z and V. Then after having done the experiment and getting values of Z and V, then we test whether it is correct by drawing a graph of 1 over Z squared against 1 over V. If that graph is a straight line, then it means that this equation is valid, because according to that equation we arrived at this stage here. So it is valid if the graph that it produces is a line. So that's when you tell us now which graph to plot. You plot a graph of 1 over Z squared against 1 over V. Relationship is valid if graph is a straight line. Obviously, this graph is a straight line, then the relationship is valid. You don't say passing through the origin. There are instances when you must say passing through the origin if the graph, if it did not have this extra thing here, which is the y-intercept. If it did not have this, then you would need to write your statement and say if it is a straight line passing through the origin. Now, here I just wrote how to find B and how to find A, but I did not justify how I arrived at that. So I must justify how I arrived at that. Now, as you can see, we want to find B, but how do we find B? B corresponds to the y-intercept. So in other words, we are saying that C, the y-intercept, is equals to 1 over 2hb. So swapping B, then B comes here to become 1 over 2h times C, the y-intercept. This is what we have here. Then next is A. How do you find A? To find A, it's not that tough, but since we already now know how to find B, then we say A, if you care, gradient here corresponds to this one. So even if I use gradient as small letter m, this should not confuse you with the capital letter M on the other side, which is what actually HAB. So BHA, like that. So I can swap on now because I want to find A. To find A, would then say capital letter M over B H small letter m being the gradient. So this is what we wrote here. To find A, we say BH times the gradient. So that's how we do it. Now finally, the final stage of the experiment each time is called the accuracy improvement and safety precautions to be taken. It has a lot of marks this stage. So we must write everything that we can think of as an accuracy improvement technique and everything that we can think of as a safety precaution. So as an accuracy improvement technique, the first one says put a sandbox underneath the beakers to cushion their fall. Now remember, these are beakers made of glass. Do we want them to break when they hit the surface? No. So we have to put a cushion. But the cushion in this case is a sand tray. It's a tray with sand. Yes, as a tray with sand works perfectly as a cushion. So this is a safety precaution, number one, to protect the beakers. Well, safety precautions are meant to protect the apparatus and also to protect the one who is performing the experiment. Then another safety precaution, wear gloves to avoid contact with oil so that the experiment does not become greasy. It's a safety precaution because imagine if you are handling the beakers, but now your hands are now oily. When you're handling the beakers, but your hand become now oily, it will mean that whatever you touch on the apparatus and the likes will also become oily. Everything becomes oily, and things will start becoming slippery and the likes. But if you use latex gloves, this can make you to avoid contact with the oil itself, which might sometimes be harmful, number one. Number two, which can actually be causing everything to be slippery. Then finally, another one, use a fiducial marker. In this case, our fiducial marker is a light gate clamped into position. Why? Because those light gates, they are ensuring that each time we release the beaker, we are releasing it from the same position. So our light gate in that case is working as a fiduciary marker. But had you chosen a different way of doing the experiment, let's say actually using a stopwatch, you would need to have a fiduciary marker. A fiduciary marker is a point whereby we can always be assured that this is where we are going to drop, or this is where we are going to start our stopwatch and drop this object from. That's the fiduciary marker. Then repeat measurements of z, with z the dependent variable, for each value of v. So each time we have a volume of oil in the beaker, it is advisable to repeat again, to drop the beaker again with that same volume of oil, and then recalculate again the value of z, and then we average the value of z. Actually, this is advisable for every experiment that you're ever going to write question number 1. You must always write about how you are going to, for every value of the independent variable, of the dependent variable, whatever the dependent variable, in this case the dependent variable was z. So the dependent variable in this case was z. But for every dependent variable, you must repeat. So you must repeat measurements of the dependent variable for each value of the independent variable, and then you average the dependent variable. You are safe as long as you are going to say that statement every time in every paper. Then finally, use a large value of h to increase the time of fall of the beaker. So if you want to make sure that there is not the time that we are going to do the experiment, because remember, if the beaker falls a very small time, there are bound to be errors. Even with the light gates, there are going to be errors. The light gate, of course, is more efficient than the human, because a human has a reaction time error to start the stopwatch and then to stop the stopwatch, which introduces errors. But a light gate is more efficient. But still, you to make some reaction time error for itself, the light gate, which will introduce some small error. But imagine if the error is, let's say, 0.01 seconds. If you drop the beaker from a larger height, the time of fall, let's say it's 5 seconds. 5 seconds plus 0.01, it means that the error is insignificant. So by increasing h, we have made the error on the volume of the beaker to be insignificant, which improves the accuracy of the experiment. So